Alternating series, video 1. I'm going to start with a definition, what an alternating series is. We say that a series is alternating if the terms of the sequence can either be written out in this form or this form. We're making an assumption that the bn's are going to be non-negative. Non-negative bn, coefficient -1 to the n plus 1. If n is equal to 1, then these terms would start positive, then negative, back to positive, negative. An alternating series where the an's are written out in this form would begin negative, positive, negative, positive, and so forth. Alternating series. In this video 1, we're going to look at the alternating harmonic series as a prototypical example showing that despite the fact that the harmonic diverges, and the harmonic is diverging because the an's are not going to zero fast enough, by alternating, there are going to be consecutive terms canceling out, resulting in the sum being finite. Okay, what picture do we have here? Well, if we add in the first term as a positive, and then add in the next term, but the next term is a negative, then we get the effect of subtracting. Then going to the third term, we would add in a positive. The fourth term, we would add in a negative, and so forth. So here it is, again, the first, and then the second, and a few more, and remember that this would represent an odd indexed, another odd index, another odd index, another odd index, another odd index, and so forth. Bring in a few more. So on the left, we're going to have even indexed, and on the right, we're going to have odd indexed partial sums of the alternating harmonic. And you want to notice that the red dots, in terms of their location, are becoming smaller, but that the blue dots, in terms of their location, is becoming larger. In other words, we want to apply the monotone convergence test to both of these sequences. Recall that the monotone convergence theorem also requires that the sequence be bounded in addition to being monotone. All right, we'll first look at the odd terms and then look at the even terms. Let's start with a simple observation. Here we have an integer, 2k, that's even, and then here's the next integer, which happens to be odd. The key thing to note is that here, that's a large value, and there, that's a small value. So that when we reciprocate, we get an inequality in this direction. So taking the large guy and moving it to their side would result in a minus on the large term. Added with a small term results in that difference, or sum, depending on how you want to look at it, as being negative. Good. Okay. Let's take a look. Let's establish that the odd indexed partial sums is monotone decreasing. In other words, that the picture is a good picture. All right. If we start with some odd indexed partial sum, and we want to go to the next odd indexed partial sum, we need to add in 2 more terms. Consecutive odd numbers are 2 apart. So if we stopped at the 2k minus first term, we would need to add in the reciprocal of 2k and the reciprocal of 2k plus 1. And remember that it alternates, so when we add in, one will be added as a negative and one will be added as a positive. Again, by the previous slide, this guy is large in comparison with this guy. Therefore, having a negative on the large guy would result in the sum being negative. So if we're adding a negative quantity to something that we already have in order to produce the next value, then the next value will be smaller than the previous value. Monotone decreasing. Fantastic. MCT requires two things. Requires that it be monotone, and we're showing that the sequence is monotone decreasing. We also want it to be bounded. All right. Well, we're doing odd indexed terms. Here we have a number which is smaller than the next denominator. Therefore, this quotient, this reciprocal, is larger than that reciprocal. Their difference is therefore positive. Here, this is clearly a positive term. Thus, this total sum is positive, bigger than 0. And we can verify that this is the odd indexed partial sum. Here are the first few terms. So letting n equal 1 would give us 2 minus 1 is 1. 1 over 1 is 1. And n equaling 1 would give us 1/2. And then there's that difference. And then we want to go out to the 2k plus first reciprocal. And notice that this sum stops at the reciprocal of 2k. Nice. On the previous slide, we showed that the sequence is monotone decreasing, and here we're showing that it's bounded below. Therefore, it has a limit thanks to the monotone convergence theorem. Sweet. That's one done. The odd. Let's take a look at the even. So on the even, we want to do the opposite in a sense. Show that the partial sums increase, but that they are bounded above. Okay. So again, suppose that we have a previous even indexed partial sum, and we want to go to the next even indexed partial sum. How do we do that? We take the 2k minus 2 and add in the next two terms. But the 2k minus first reciprocal will be added as a positive, 2k's reciprocal added as a negative. And since the reciprocal of a small number is larger than the reciprocal of a large number, then this term is positive. So what we began with, we're adding in a positive quantity, resulting in the next term in the sequence, so it's larger than the previous term. Thus, we have an increasing sequence. Good. MCT also requires boundedness. Because it's increasing, we're interested in being bounded above. Nice. So to show that it's bounded above, remember that the alternating harmonic series begins with positive 1. The next term would be minus 1/2, letting n equal 2. 4 minus 2 is 2, and we have negative 1/2. The term after that would be positive 1/3. When n is equal to 2, we'd have 4 minus 1. There's 1/3. Good. And again, the notion of here's a small integer and here's a larger integer. Therefore, this quantity is large compared with that quantity, i.e. their sum is negative. The last term, negative 1/2, that's negative. Thus, we're taking 1, and all of this is adding in some negative quantity. we found that the alternating harmonic series has partial sums whose even terms are increasing bounded above, therefore converge, whose partial sums which are odd indexed are decreasing and bounded below, therefore converge. To clearly see that they're going to converge to the same limit, we can express an odd indexed partial sum as an even indexed partial sum plus the next term. As k goes to infinity, this next term goes to 0. And as each of these are convergent, they must both, therefore, go to the same limit. In this picture, the limit would split the difference. Excellent. Hence, this alternating harmonic series is a convergent series, whereas the harmonic diverges. And again, it's this notion of we add in and then immediately subtract away. Add back in, immediately subtract away, add in, subtract, add in, subtract, add in, subtract. And the amount that we add in or subtract is smaller and smaller. Very nice. Excellent.